Dimitri gave the nice introduction and mentioned that Levi kind of outlined these metal organic complexes and different functionalities to them to try to tune their photoluminescence properties. So the two functionalities are, one of them come from substituting this R group on the top of this metal organic structure by varying electron donating and accepting groups, so from 1 to 5. And then also functionalizing like the conjugated carbon backbones with where these dotted lines are. And so the three different functionalizations for those is Na, which is nothing, so it's just vacuum in those spots. C2H4 group, which would be a non-conjugated portion, and then C2H2, where it would be fully conjugated.
So A has hydrogens off of those carbons.
Okay,
so
yeah.
It's not vacuum.
So it's capped with
Yes, okay.
hydrogen, which you'd expect, and then, but yeah, there's in between the hydrogens, it's vacuum. So the main point is just testing the structural rigidity, because if you just put more carbons in the backbones, you'd expect it to have less rotational degrees of freedom. And so overall, it gives 15 compounds to run calculations on, and Levi did quite a few of those, and those are summarized here. So essentially what he observed.
May I ask before we go further?
Yeah.
So what would be the right name for this geometry? It's not really square planar, right? It's not a planar complex.
It's
so for A, it's like a distorted square planar or tetrahedral. And then for B and
tetrahedral or distorted square planar, because they actually different geometries resulted on a different D energy.
Yeah, so I would say it's a distorted square planar.
Okay, so it's really more planar rather than tetrahedral, right?
Yeah.
Yes.
And it's the more structural rigidity, the more planar it gets. So like the A compounds, like those ones show the most like distortion. Like sometimes you can kind of see it wants to get the tetrahedral, but just due to sterics, like it can't get there. So it stays closer to planar than tetrahedral.
Yeah, and the other thing is, so the dihedral between the pyrene and the phenol, that would be a pi dihedral, so that would want to be around 38 degrees or something. So that also doesn't really allow for the tetrahedral organization.
Okay.
So I guess moving on from the structure, like the main insights that Levi saw from his calculations were that when you increase the electron withdrawing group, so going from 1 to 5 with those substitutions, they saw a consistent redshift in the absorption and luminescence spectrum. And then with increased structural rigidity, so increasing like the conjugation or delocalizing the wave functions on the carbon backbones further, induces the redshift. So the structural rigidity, that makes sense to me because you're just increasing your confinement, which you would expect a redshift. The electron withdrawing group inducing redshift, that's not as intuitive to me, but it's a clear trend where you can see that's in this middle panel, like from 1 to 5, there's a bigger.
Yeah, so Aaron, for this is kind of a 2-stage project. So the first stage, we only looked at the electron withdrawing nature. And the main takeaway that from the paper that we are currently working on is the LUMO is destabilized when you put the electron withdrawing group, which closes the band gap. So that's why it redshifts for electron donating to withdrawing.
Okay, I think I see what you're saying, but I have some orbitals plotted, so we'll get back to this question about changes in like the LUMO once I get to the orbital section. And so these are trends that were computed from Gaussian calculations, which uses TDDFT. And well, I guess before going on to that route, the next motivation for these complexes is to see how well they could emit photoluminescence. And that requires computing radiative and non-radiative relaxation rates for the HOMO-LUMO level, essentially. And so the motivation is to compute dynamics rate constants, which isn't available in Gaussian. So we wanted to check to see if these trends stayed consistent if we implemented them in vast software where we can compute dynamics. And so that's what is shown here, testing different functionals. And then I guess the takeaway summary is that there is a certain subset of the vast calculations which follow the same trends from the Gaussian calculations. So the 1, 3, and 5 compounds, which is changing the withdrawing groups. And so it's these 9 compounds that were selected to do dynamics for. So that's what I'll move to next, doing dynamics. So the first thing I'll show is the 4 closest orbitals to the band gap. Those are the most primary orbitals that will see happen during the dynamics. So I guess the way to read this is going from left to right, that's changing out the withdrawing group. And then going top to bottom is adding more structural rigidity. And the consistent things to observe from the orbitals is that the HOMO -1 and HOMO and LUMO +1 orbitals are very similar for the 1 and 3 compounds. So with the amine and styrene attached. But the orbital structure starts to change with the NO2 group functionalizing. Specifically for the LUMO, it seems that in the LUMO, the withdrawing groups pulls most of the orbital density away from the ring. Whereas with the other group, with the other functionalizations, there's still a large portion of the density localized on the conjugated part of the molecule.
Aaron, may I ask?
Mm-hmm.
So from the orbitals from LUMO +1, it looks more like S orbital rather than D. Other, like any information, what's the character of this unoccupied?
So it's
like from PDOS or from some other sources?
So it's more like a dumbbell facing us if I rotated it.
Mm-hmm. Okay.
There's no density going into the page. So the density is coming straight out. So it's not S, it's more dumbbell.
More like P.
Coming out towards you.
square,
Right.
right? DZ square has this kind of shape with a little bit in the center.
Mm-hmm. Although,
And-
yeah,
And it could be that the DZ squared is hybridizing with the p orbitals of the nitrogen and oxygen.
Mhm.
So it then takes the donut and makes it 4 localized portions.
Okay, makes sense. Yeah, thank you.
And you should be able to see that Luma +1 higher in energy for the 5 compounds, or at least when I looked in Gaussian, the Luma +1 was a higher state for 1 and 3, and the electron withdrawing pushed it down.
I think,
But
okay, well,
but that's not needed information.
yeah, I think we'll see that on the next slide. So I guess since we mentioned it, so these are the ground state orbitals for the optimized structures. And then to start dynamics, we do molecular dynamics at temperature. And I plotted the orbital or the energy fluctuations along the trajectories. And so in each panel, it should identify which band's HOMO and LUMO.
Is it only my computer, or are we still on the same slide?
On
Oh,
my
Okay.
So I guess I don't know. The main takeaway here is that one of the consistent features is this kind of band with high variance, and those are the LUMO +1. So those are associated with the transition metal. And then the bands which have fairly narrow fluctuations, those are the ones that are located mostly on the conjugated ring. And I'll mention again that comparing like the 1 and 3 columns, their bands are fairly similar, but when looking at the 5 compound, so the most electron withdrawing, it seems that VASP introduces an additional state which is lower than the orbitals localized on the transition metal. I think this is what Levi was mentioning just a couple minutes ago, where the withdrawing group was pushing some of the bands from the ring lower in energy than the transition metal. Is that right, Levi?
Yeah, and I think this clearly demonstrates it. So yes.
Okay. I guess the important thing to take away is that there's easily identifiable HOMO and LUMO states, and there's not a significant amount of orbital swapping going on during the trajectory. And so then this will lead us to the most compelling data for these structures. And so on the top left is just a diagram, just reminding us what all the numbers and letters mean. The top right panel are the non-radiative relaxation rates for the HOMO-LUMO transition. And then the colored boxes correspond to the boxes on the left with the structures. So top right is non-radiative, bottom left figure is the radiative relaxation rates, and those are averaged over the trajectory as well. And then the bottom right figure is the photoluminescence quantum yield. So it's the ratio of the radiative rates for the non-radiative rates. And I guess the thing that stuck out to me is that the A and B compounds, so for the luminescence quantum yields, so the bottom right figure, the 1 and 3 functionalizations, so the green and red box, they kind of follow a similar trend.
Aaron, would it be possible to copy and paste the VASP absorption onto this slide? I think it's slide 6.
This one?
And then this was PBE.
Yeah.
Oh, it's taking a moment. Yeah. So, and the only reason why I say this is it may be important to remember that the energy difference will greatly determine like the gaps law. Okay, sweet. Thank you. And you can make it a little smaller if you need.
Yeah, that should fit.
Okay. Sorry for interrupting.
Yeah, I guess what I was mentioning is that the trends for A and or the 1 and 3 functionalizations, they showed a quite similar trend where it's A, like A starts in the middle, B shows the peak yield, and then C shows a pretty significant dip. Whereas the most withdrawing compound kind of showed a different trend where it's going from A to C, it peaks and then goes to the minimum. So I think the reason that 1 and 3 are comparable is because their orbitals are relatively the same regardless of the functionalization. Whereas with 5 is the very heavily electron withdrawing group. It kind of changes the characters of the orbitals. So the trend kind of gets thrown out of whack, but I think it's a good sign though that the most with electron withdrawing group, they show the lowest intensity non-radiative and radiative recombination rates. So they're smaller compared to like their analogous compounds, which makes sense because since there should be less like orbital overlap between HOMO and LUMO for the heaviest electron withdrawing group.
Microphone.
Is it true that also 5A, 5B, and 5C are the most redshifted comparing to the 1 and 2?
One, yes.
Yeah.
Okay, so then it looks like this addition of conjugation on whatever this position with which is shown with this dotted line is really redshifting the lowest energy states with MLCT, strong MLCT character. But then we have reduced quantum yield, reduced quantum yield emission. And it's not just because the radiative pathway is increased for this case, but it's also radiative is reduced as well, right? So what I'm trying to say, I'm a little bit surprised that we have radiative rate is also suppressed comparing to the less rigid or whatever, less conjugated structures, which I would say you kind of explain it because we see that it's really moving, the orbitals are moving to this R position, right, to this additional ligand position. But usually pi conjugation should also increase the delocalization of the orbital along this pi conjugated path.
Mm-hmm.
So,
Yes.
so that's why usually, like it's, I saw the papers where they talk about copper compound, copper 1 complexes, where they discuss that, yeah, addition, it's a different ligands, also including some nitrogen's coordination with copper, but they also see this effect that they can shift, significantly shift to the red, the transition, the both absorption and emission band. But then due to the increased conjugation part on the ligands, but the emission was significantly reduced. And they kind of explain it through the non-radiative processes. Of course, it's many experimental papers. They don't really do any computational part on that. So they really try to explain it through the non-radiative, like increasing the non-radiative rates. Again, if you're shifting it more to the red, you have stronger complex with phonons and so on. So, but I think what is really interesting for your calculations, that, yeah, you're showing for sure that that it's not so much on the non-radiative pathway, because non-radiative pathway are actually smaller comparing to the other cases 1 and 2, but it's really radiative pathway is reduced.
Mm-hmm.
Aaron, did you do a scissor operation to correct for the underestimation of the band gap?
Not for the dynamics.
Yeah.
Because I thought when Svetlana, Dmitry, and I, and maybe you discussed it. No, I think with Dr. Soon, we looked at the three PBE for Gaussian, PBE for VASP, and then PBE 0 for VASP. And we went with PBE, assuming that there was going to be a scissor operation to take it from like 0.5 electron volt to like 2¼ electron volt. And I didn't know if that would change any of these results.
I guess in my head, it's like, I guess there's two different ways you could compute couplings. You can compare like energy differences along the trajectory, or else you can compute them from the orbitals. And then I guess our method, we compute them directly from the orbitals. So there's no really energy input.
But okay, I guess using Tolley's surface hopping, there is a term for energy difference. And that would dramatically change.
No. Oh.
What?
Yeah, but this also related to the other complexes, right? So we expect that this shift in the energy is systematic for all complexes, right?
Yes.
Yeah, we are underestimating the gap, but this underestimate is roughly the same for all three of the for 1 and 2 and 3 and 5. I mean 1 and 3 and 5 cases.
Okay.
One can try to make this correction later, but maybe for the first shot, let's keep procedure as simple as possible.
Okay. I just
Levi is
wanted to get everything straight in my head.
Yeah, Levi is on the right kind of side of the question. So of course, if we have more redshifted energies, because I think in because this is PBE calculations, not PBE 0, right?
Yes.
Yeah. So if we just look on your values for the absorption spectra, right, and compare with Gaussian, so Gaussian gives this low transitions. I'm just look on the red line, right, around 2, I guess, electron volts. PBE 0 gives it also even more than 2 point something, but PBE gives it around 1. So you already have 1 electron volt more to the red rather than it's supposed to be.
Yeah, and I believe that the gap law has a power of 2. But the interesting thing, if you look at 3A, it's about 75% for the PL, quantum yield, and the experimental paper for that compound says it's 76%. Which is a very good indicator that the method is working.
Yeah, but on the other hand, again, if you look on the so am I understand correctly that this top panel in this insert where you have G16 PBE 0?
Yeah, that's been Gaussian.
Yeah, this is Gaussian, but this is single calculation for Gaussian, or it's not a TDDFT?
It's T to the FT.
Oh, but then why is it so different from? Oh, I see. It's absorption, not emission. Okay, because emission is actually at around 1.5 rather than 2.
Yes.
Okay. Yeah. So I'm trying to say that if Erin, can you go up one slide with this dynamics changes for the orbitals when you were showing this many lines? And I guess we need to wait until it moves because it takes some time to, because we're still on the old slide right now.
I moved it, so
Oh, yeah, it just goes with a delay. Yeah, so I think since this is the results of the dynamics, so yeah, so technically your estimated emission energy will be around what? Around 1 electron volt, right? If you look HOMA-LUMA gap at the very last moment of your time.
yeah, they're approximately the same as the ground state calculations. So looking at the bottom panel of the absorption spectra.
Yeah. So which means again, so if we really take these energies and compare with emission energies, the energies which Levi got from TD-DFT optimized, right? Geometry for their emission. The difference now, it's still more redshifted compared to the predictions, but now it's a little bit less than 1 electron volt. Yeah, so I'm just trying to say that this arrow, first of all, is supposed to be systematic, so which means if we compare in between each of these complexes, the rates should be kind of getting the same arrow, right? On one hand. On the other hand, this arrow is kind of a little bit self-healing if we compare not absorption but emission, because emission is more redshifted comparing to absorption in Gaussian calculations when we optimize the excited state. Okay, but I think it's kind of interesting and maybe counterintuitive and contradicting observation or observation from your results that increase in conjugation for these complexes, for these ligands, not so much affecting non-radiative pathway, but radiative pathway. And again, you explain it because it's really, since it's a strongly electron.
It's localized, not delocalized.
This is electron withdrawing group, right? Strong electron withdrawing group. Yeah, so it's kind of results on a more localization rather than delocalization. Although intuitively we expect that it has to get exactly the opposite result.
Yes.
But is it the same when you do DFT with a local basis and with more advanced PBE 0 functional? You see the same trend, right? So it's more localized towards this R group rather than on these conjugated parts?
Are you asking me or Aaron? If you're asking me, I
Levi, yes.
believe when I did M062X, the trends were qualitatively identical.
I don't understand what is M06X.
It's a hybrid functional that's supposed to be really, really good.
No, I'm just talking about PBE0 functional. And you look on your orbitals for low states, right?
Yes.
You saw the same trend or not, that you have more localization?
So S1, when you run T to DFT, is a homo-lumo transition. There's no hybridization.
Yes, but my question is where your orbitals are localized.
It's delocalized for 1 and 3, and then it's localized for 5.
Okay, so it's the same trend as Erin was talking with, showing his orbitals with his VASP calculations, right?
Yeah, the orbitals look very similar between Gaussian and VASP. And then for T to DFT, S1 is a homo-lumo transition.
Okay, so it means again it should look very close to this single particle orbitals.
Correct.
Okay, good. Yeah. So then we can explain why so we can trustably, hopefully, explain this reduced radiative rate for the strong electron withdrawing groups.
Yes. The only question then is, why does the C compounds for 1 and 3 go down? Because you would assume that would be more electron delocalized compared to the A and B. But there's a pretty significant decrease in the quantum yield, and that may be due to decreasing the energy for the transition, making the gap law say with lower energy transitions, it's less emissive. So going from B to C, you lose quantum yield because you reduce the energy.
No, you not reduce them.
Wait. We discussed it, I think, and Aaron, would you like to comment? Maybe you just relation to the ratio of radiative to non-radiative.
Can you say that again?
So Levi seems to ask about point attention onto interpretation, why the complexes C have smaller quantum yield than B.
I guess in most cases, B shows a higher radiative rates than C. Well, I guess for the 1 and 3 functionalizations. And they also show
I
lower.
understand that it's the radiative over the sum of radiative and non-radiative. I'm trying to interpret the final results from like a chemist's point of view.
But you started, well, both of you started the thought. Let's maybe Aaron complete it. It will connect the loose ends together.
I'm kind of lost on I think the question is going from B to C. So with just the increased conjugation, why there's the D. There's a general trend of decreasing yield across all sets. Is that the question?
Yes.
So in all cases, going from B to C shows the drop. And in all those cases, there's increased conjugation along with increased electron withdrawing.
So let's forget 5 for now and only look at 1 and 3, right? So 1 and 3 are similar. There is some changes. If we look at the radiative relaxation, A and B are very similar, where C drops in its radiative relaxation compared to A and B. And then for non-radiative, B is the lowest, and then A and C compete for which one's the highest, which then leads to B being the lowest because you add a smaller number. So it's closer to 1 for B in both cases, where when you go to C, due to the radiative relaxation rate dropping compared to B, for like comparing C to B, you drop the radiative relaxation, but your non-radiative goes up, which causes your quantum yield to go down. So that mathematically makes sense. Now I'm trying to interpret this data in a way that would be meaningful in a publication. Does that make sense?
Yes, but there one can try to add another chain into this train of thoughts.
Okay.
So why non-radiative is higher for C compared to B?
No, but I think he's asking backward. He's not. He's asking. It looks like if we compare 1 and 3, the radiative rate for C is slow comparing to B, and it's similar for both cases, 1 and 3. Am I right? Levi is asking more about why radiative is.
Yes, but Dimitri's question is also valid. So Dimitri is asking, why is non-radiative rates higher for C compared to B? Correct, Dimitri?
So how does gap in C compares to B?
It's smaller.
For
And
C,
in some cases, it's significantly smaller.
for C, it is smaller than for B.
Yes.
So then gap law is responsible for non-radiative being quicker.
Okay, so then what you could interpret is for C, the structure does not vibrate as dramatically, but due to the gap law, it has a higher non-radiative relaxation. And for A, the structure is much more it's less rigid. So due to more vibrations, that causes higher radiative relaxation. So B is the Goldilocks range, where it reduces the structural vibration while keeping the gap, HOMO-LUMO gap, sufficiently high so that the gap law does not kill the, does not increase the non-radiative relaxation.
I like this interpretation. Thank you. Aaron, what do you think about last 5 sentences by Levi?
Makes sense to me.
Okay.
And then for 5, the rationale is due to the localization on the head group that reduces the radiative relaxation, causing it to be a different trend than 1 and 3.
Mm-hmm. And the localization mostly affects the unoccupied orbital. So it's
Yes.
it pulls more from the LUMO, so that's why it gets darker.
Yes.
Whereas the HOMO still stays relatively delocalized.
Yes. And then due to that localization, the non-radiative trend is also changed because the flexibility of the pyro to the phenol is not an issue because the orbital is not located on that. So that's why we don't see a high for A, decrease to B into the Goldilocks, and then an increase due to gap law. Is that a justifiable interpretation? Okay.
Yeah, that's what
Sweet.
I kind of pulled from staring at the data for tens of minutes.
Does anyone, never mind, it's Aaron's presentation.
Yeah, I guess if we're all reasonably happy with that, that's the main contribution from the calculations. I did try just one other thing, seeing if I could replicate Levi's line shapes for the luminescence. So we have this molecular dynamics photoluminescence protocol. So basically it's just extracting the PL energy and oscillator strength and then plotting that over time. And that's what's shown in the left panel for the C compounds. And the 5C actually compares fairly well with what Levi saw with the side bands, but the side bands were missed for 1 and 3.
I have a suggestion for a cheesy science publication. Let's take only 5C complex and send paper to Nature with a great agreement with all methods.
Aaron, what's your line width? Is it really, really small?
Yeah, so it's, yeah, I make them small because if it's like the normal line width, it just, because I'm basically plotting like 1,000 transitions. So that, yeah, the widths are small to make like the scale look reasonable.
So I know that we talked about this, and I think it's either not an issue or is being swept under the rug. But for the line shape, it may be important. Do you remember when, so I gave you the distorted square planar, but for the, as you went in your MD, it went to more square planar. Would taking like the last half and replotting this do anything? Because it may, can you go back to, never mind, I'll just look at my, I have your slides open. No, never mind it. It doesn't change anything from the electronic point of view. You can disregard that.
Okay.
I have just a question. Is it possible to implement the PBE0 functional for the dynamics? Like, because if I understand correctly, for your dynamics, what we really need, we need the recalculate at each moment of time, recalculate the couplings, right? The non-adiabatic couplings. Is it possible to and you do it with a single point calculations, because you already take the geometry from the dynamics. So you run actually the adiabatic dynamics is run with PBE GGA function, PBE, right? And then you recalculate each step for the couplings with PBE0 functional. I know it's much longer, but for these small molecules, do you think it's doable or not? Like, because I have no ideas how long it takes to do this dynamics and to do this non-adiabatic couplings calculations.
Yeah, so the dynamics is quick because that's just running molecular dynamics. I think with PBE, I think the calculations ran within like less than a week for sure.
Okay, if we can recalculate it with PBE0, we don't need to do it for 3. If we can take like one complex and let's say 5, which is the most redshifted, right? Where we expect that there might be really the issues with too much redshifted energy, 1 instead of 1.5, right? So if we can recalculate it with PBE0 and get pretty much the same data, but with the right energies, I think this would be very convincing proof that this constant shift of energies to the red due to the not very good functional is not really an issue.
Mm-hmm.
And again, I have no idea how possible it is, because it might really takes forever.
Well,
So when you calculate your rates, how so how long you how many snapshots you, so you really take in all this 1,000, how much you have, 1,000 femtosecond, 1 picosecond rate,
They're doing Green's field.
right? But still they calculate their couplings based on regular, same as we doing, right? So just overlapping the orbitals at each moment of time, right?
mm-hmm. Yeah, so for these trajectories, it was 1,000 femtoseconds, so 1,000 structures.
So it means you calculate your non-adiabatic couplings for the entire trajectory from 0 to 1,000.
Mm-hmm.
Okay.
Yeah, so it's,
So it means you really need to go now each point for each 1,000 data grid, you have to recalculate it with PBE 0, right? Instead of PBE for couplings.
mm, yeah, I think it's been a while since I ran the calculations, like just to do optimization, like it didn't seem to take like very long time difference, but
You mean
yeah, then when you add 1,000 calculations,
PBE
I'm
versus
not-
PBE not, right? You
Yeah.
say long for PBE versus
yeah, I mean, it might have been like, I can check the output files to see the exact time difference,
Mhm.
what it was, but I'm sure it didn't seem like more than like a factor of 5. So then I guess
yeah, so
like
just a suggestion, right? So maybe of course we are not going to do it with how many structures you have, 9 structures, so we don't want to do it with 9, but you can choose one. I would say let's take the one which is the most redshifted, which I think is 5C, right? 5C is the most redshifted.
And it agrees between different methods, so it's I really support further investigating it.
So yeah, and let's if you recalculate it now, like you not need actually to run adiabatic dynamics, because you use the same geometries from adiabatic dynamics, right? We're assuming that adiabatic part is okay. And then just recalculate the couplings based on the PBE 0, which of course also will give you new set of energies, more blue shifted energies.
mm-hmm.
Energies, couplings, and then you go through your Redfield theory, right? And see whether you will see different rates or not.
Mm-hmm. I see exactly what you're saying, and yeah, a lot of everything's already set up, so it's just changing the in-car file essentially.
So Svetlana and Dmitry, would he just do 5C, or would he have like 2 data points to compare?
No, 5C would be good enough, because he can take quantum yield, right? So it's radiative versus non-radiative, put it the ratio between them. So yeah, and to see how much quantum yield is affected. If it's affected by, I don't know, 0.5, no one cares, right? But if it's affected times how many, a little bit smaller, a little bit higher. But if it's really twice, 3, 10 times difference, then it's an issue.
Mm-hmm. Yeah, I think the first thing I'll do is just look at the orbitals first, because if the orbitals are like
Different.
the ordering are the same, it's like I wouldn't expect there to be drastic changes in the rate constants.
Yeah, but Levi is right for couplings, because again, don't forget, you always increase your rates if your coupling is increased, right? And for couplings, there is a ratio, the energy difference, how to say, the matching between energies of splitting in the levels is in a formula, and I don't remember.
I thought it was in the denominator.
This is what I also think. So in other words, if your energy is, instead of 1 is 1.5, it might affect the couplings beyond just the orbital overlap, right?
Mm-hmm.
So yeah, you're right. You can, of course, the easiest way would be to take a look on your orbitals but I think since the answer for orbitals is we kind of know, because Levi also said that with his Gaussian calculations, both TD-DFT and just ground state orbitals look similar to yours.
And I use PBE 0.
Yeah, and he using PBE 0. So that's why I think if you, it makes sense to compare your calculations, but I think especially you probably already have it since you were calculating your absorption spectra with PBE 0. But I think it gives you the answer which we already know. They will be they may be not exactly identical, but very similar in overall trends.
Mm-hmm. I see what you're saying. It's just, yeah, that was just mostly, I don't like, well, I try not to get surprised when I'm running calculations. So if I see something's horribly different than what I expected.
Yeah, for sure. This would be the first step. But as I said, like to this, be 99% sure that you will see the same picture. And I think for the question, how much really your rates will be affected if you're really shifting the energies, and plus maybe a little bit change to the orbitals. This is, I would say, I would not put 100% or 99% accuracy that, yeah, nothing is really changed. So this might surprise us. And you probably can just start doing this if it doesn't require, yeah, I don't know, if it doesn't require change the codes or anything, then it's not really a big issue to rerun these calculations with a different functional, right? I mean, only couplings. You need just to calculate the couplings. You don't need to run the dynamics with it.
Yeah. Yeah. Most of the time is just waiting around in the queue.
Or you can, I don't know, 1,000 jobs, because you already have all the geometries. You can really put all 1,000 jobs at once.
Svetlana, I thought that you previously said VAF takes a few iterations to get a stable wave function. So that's why we have to have the overlap when we split it into several jobs.
Yeah.
But I don't know.
Yeah. I guess normally they speed them up. I'd bin them into like groups of 100.
Yeah. Yeah. Well, of course, I was just putting these numbers just saying. You definitely
So Aaron, on
them
slide 12, I do have a question. I don't know if you were going to slide 12.
Let's just keep natural train of presentation.
Oh, this was at the next page.
Yeah. So
it's still okay.
Yeah, this is what we were. And then this was just preliminary looking, seeing if there was anything interesting. And,
so my question relates to the two blurps between the initial and final state. Are those like Lumo +1 and Lumo +2, or are those the same states, but due to time, they vary dramatically?
No, they would be different states. So like the very top one, that's like Lumo +8 or something. And this rung here is like Lumo +5, and then this one's probably like Lumo +1. Okay. So it just has like an intermediate lifetime in these states. And I guess I don't really have anything interesting to say about them because the.
So does that mean that the Lumo +1, or the state that is localized primarily on the what we think is a DZ squared state, is not showing up because it does not have sufficient overlap to have high coupling, so it just jumps that state?
That's one possibility, but I think this rung here would be that DZ, because like on average there's like a fairly large subgap.
It's about, if I'm looking at your slides, it's about 0.75 electron volt, if you take the average, right? So you take the average of each state to plot here, right?
Right.
So
yeah,
it's like 1.75. And
yeah.
that, oh, I guess, yeah, that would be Lumo +1.
Yeah.
Okay.
And maybe it will help to fix the slide number 11. So it will create the substructure, not from the Frank Condon factors, not from the geometry, but the emission from metastable states will make the photoluminescence profile more structured with several contributions. Like for assessment of, for validation of the methodology, maybe one should compare it not only to other style of calculations, but to experimental emission, right?
Yeah, and I think for these series, the only experimental one is 3A.
Mhm. And we do not have power to speed it up,
Speed what up?
to speed up generation of experimental results.
But
So
experiment,
not really, I don't think.
Okay.
you're asking about experiment?
Yes.
No way.
Yeah.
Yeah, I think Wei-Feng was just talking about her graduate student. She's kind of unhappy with him, with his productivity. So I think we should, and she has really not many people working right now in her group. So
And
I think she's not able to get these measurements right away.
yeah, and when I was looking at the synthetic routes, it seems like they're relatively straightforward, but too complicated for anyone in this meeting to do.
So I have another suggestion. Maybe you need to show, like here, you're just showing the adiabatic kind of how to say the results of non-adiabatic dynamics, right?
This
Intraband.
figure.
Yeah. So this is just intraband dynamics
Um,
separately for electrons and holes. Am I right?
so intra, and we also introduce like a dampening factor. So you see like the yellow and blue lines, those fade away. So that's the non-radiative recombination. So populations are damped along the excited state.
Yeah, but can we present it through? I think Dmitry was showing these presentations like instead of showing home and luma or whatever, your occupied, unoccupied states separately, you can present it as a exciton and show how an exciton is moving this time. Well, same dynamics, but for the connected electron hole pair. Is it possible? Yeah, am I right, Dmitry? You were showing something like that before. Of course, for other systems. You were showing not just homoluma, but
Everyone understands what we are talking about.
so because when you include this kind of exciton, if it's dark, we will not see it, right? If the oscillator strength is very weak in between this transition.
Right. Yeah, I think the figures you're talking about, it's like the energy, like the excitation energy over time.
Yeah.
So, and then yeah, that goes with our
the difference
like,
energy between your home between your initial hole and electron states.
yeah, and that's in the like the luminescence dynamics codes that we have.
And then you multiply that by the oscillator strength of each state, so that if it's optically inactive at 0, no matter how long it stays. Is that right?
Mm-hmm.
Okay.
Yeah, so it's occupations weighted by the oscillator strength.
And then centered at the energy.
Mm-hmm.
Okay.
With a little broadening.
Yeah.
Just in addition to this representation, maybe if you look on the exciton, I think interpretation would be easy in a sense. Like I missed probably the beginning of the question from Levi, but I hope that this was similar to my question in a sense that since we have these intermediate states, especially for the electrons, right? But the emission spectra which you show having just much pretty narrow line width.
Mm-hmm.
for the complex 3A. Which I would expect that this should be all like narrow and smooth instead of really having this 1, 2, 3, 4 peaks.
Yes, I think that's what Dimitri was
here we
saying by fixing slide 11.
Yeah, so it's
But I don't think we need to fix. If you just show the excitation energy, maybe it will be clear that just not all of these intermediate states really contribute to the actual luminescent exciton.
mm-hmm. And yeah, this is like not a good figure because I realize that the transition energies are like very high for a lot of these complexes since there's such large subgaps.
Mm-hmm.
So it's
Yeah, I think
so this is just a bad initial condition.
so this, but these subgaps really just follow your density of state, right? Because if you return back to the slide 9 with your shaking electronic levels, you clearly can see that you unoccupied levels. Yeah, you have luma, then kind of separated luma plus 1. Then there is many states, and then again subgap, and then again many states. I don't know. You probably cut it too early, right? For 3A, if you look on it, you clearly see that, yeah, you have pretty well, you expect there will be well distinct luma plus 1, then manifold of band, and then again it's splitted from subgap for another manifold. So this intermediate steps probably is really just dictated by this subgap splittings between these states or manifold of states.
Mm-hmm. Yeah, that makes sense.
For the holes, I think they probably, like we have these 2 states instead of many of them. Probably, although we see some kind of separation between HOMO plus 1, but still this probably not big enough in the sense that you still have high energy vibrations which can overcome this subgap, and that's why you really have only this HOMO minus 1, HOMO minus 2 contribute to one intermediate kind of shiny state, and then subgap, and then again another manifold of states contributing to another bright line.
Mm-hmm. And yeah, I guess I don't really have any more to say about them because I was just looking to see if there was anything interesting from going through the dynamics and comparing like hot carrier cooling rates between the models. But I found that you can't really I don't think it's very useful to compare the cooling rates because like a lot of the there's not a lot of useful transitions to look at because a lot of the transitions are like very high in energy. So I'm limited to like very few initial conditions, which makes sense to run the dynamics for.
Yes, and that is kind of known. So I guess the question I have is if we are planning on meeting next week to kind of figure out figures and tables for you, do Dimitri or Svetlana have specific things that they would like to see? Or are they going to leave it in Aaron's hands?
I was thinking if we will have a meeting, it would be not just Aaron figures, it would be actually yours and Aaron figures together.
Yes.
Because we need to really kind of decide on, can you return back on your main, I think the main slide would be number 10, right? So right now, yeah, and it takes time to get there. Right now it's kind of very busy. And of course it has redundant information for the paper because like structures have been shown and so on. So I think it's probably just reorganize this slide into the figure and then just decide how we go with supplemental, because we also need to have a good plan for supplemental figures, right?
Mm-hmm. Yeah, I think. Yeah, you just use nicer plotting software. Remake these 3 panels and just A, B, C.
Yeah, probably like this. So I think you can make the figure and then send it to Levi or whatever. You probably guys really need to discuss it between yourself, how you want to do it. So
Okay.
whether Erin just send you the raw data and Levi is making figure to be consistent with the style which he's using, because I think in this in the main text you have how many, 4 figures already, right? As we discussed.
I think there's 4.
Yeah.
I've kind of thrown it out of my head and I need to pull it back in, but I think there's like 4.
Exactly my point, right? So that's exactly the reason for if we meet next week or maybe next week, but as I said, like probably it's better sooner than later. So then it just kind of to refresh all the figures which we have, so we can clearly see how everything is fitting together, and also be sure that the style is not like looking completely different.
Yes.
And get to the clear plan for the supplemental. I think for supplemental, most of the figures which Erin was showing, they're already in a pretty good stage, right, for supplemental figures.
Yeah. So it's mainly just this slide, how we want to make the 3 bar graphs cohesive.
Yeah, but yeah, I guess it's also easy. Just go with panel A, B, C.
Yes.
Okay.
So
Yeah, please keep going. I was going to
we're thinking about having him do these either quantum yield dynamics so we can get the spectra features, or is that kind of a side that we don't really need to look at? So like slides 12 and 13.
Well, for now, I don't think it's needed for this paper. It just intrinsic kind of features which just explain. So all the information is just in this rate.
Yeah. Yes.
I don't think that this graphs 12 and 13 give any additional or more clear explanation of what's going on there.
Mm-hmm.
I
Yeah.
would say
8,
these
9, 10.
adiabatic lines, right? The energy for adiabatic lines probably makes sense to show.
Yeah, slides 8, 9, 10.
Yeah.
Those would be
And
without
again,
taking the main
I
concept.
just returning back to my previous suggestion, if you show the dynamics of the emission, the exciton relaxation, right? Starting with this and returning to its ground state, the exciton instead of electron hole presentation for the dynamics, right? So maybe if you redo it with the exciton, maybe it will be more useful in a sense that it will be clear what's going on there, and maybe it really will bring some insights. Maybe yes, maybe not, but at least try to make it and take a look. But I think just single electron hole pairs are not very much helpful. So I don't think we really need even to include it to the supplemental.
So let's check if there are more questions from Amir, Mid. If there are no questions, you do not need to speak or type. If there are, please do, because we are going to conclude soon. No? So this greenish figures that were recently criticized will be one of your goal for next couple of months. The ones that Erin was showing in slides 12 and 13.